Oh, Tom's got it right. Our projections.
Okay, there you go.
Or-
Yeah. I'm looking at like multi stuff and stitching and it's like,
Yes.
it'd be cool.
Watching.
Which is okay for the most part, because most people come with an Apple or a Linux. But if anybody over in geology or something like that wants to go on.
Then we're learning a
Yeah,
lot.
please, because otherwise I'm gonna rattle on when I
Learn.
You, Jeremy?
So I am and so it just connected. Yeah.
Yes, going. Good night.
It's gotten better.
Figured it out, and Kevin can help me if I goof it. Yeah, 5.
The password that's on
Well, first, I know, I agree with what already. So that'll ever be, and I'll ever be. All right. I'm presenting on the. It's gonna be interesting.
I'm on the way now on my phone.
It is. It's a true statement.
So,
You know.
turns out that the Monster catalog is a suitable drop-in replacement for Gaia DR3 at the moment because
Right.
there is a incorrect.
Gave us a lot of beers last night.
Yeah. Correct.
So,
Yeah, how do you like that?
Now it's
stepping up and now maybe it went
Well, we have way tens. That's okay. Down until.
good they are.
There's a no host.
I don't know.
A couple of gals tests.
Yeah.
Yeah. Sponsored by
A long time ago.
That's what I said. Next time there's no host.
You ever hear from
I need to go right on. I need to actually.
She and I got these mugs.
Next.
Okay, you're all done?
I think full of stuff.
You send money to WG.
Snacks are in the fridge.
Thank you.
Where else? What am I using? You're on the shelf.
Go, right.
Yeah. You just need to get a sharp one.
See, so we're meeting him.
Not last time.
Oh, I know.
Everything except last night had helped. It was very nice. It was a few of the other people.
Down someplace.
I want to get the presenter view.
That's, yeah, it's 8:30 now. All right, good morning, everyone. Let's kick off the morning session. Hope everybody's well caffeinated. Have some very exciting talks, and to kick us off, Rebecca Hounsell is going to talk to us about the future of Type 1A supernova cosmology with the Nancy Grace Roman Space Telescope.
Okay. Okay, good morning, everybody. Can everyone hear me okay? Wonderful. And first off, I want to say hello. My name is Rebecca Hounsell. Thank you for the introduction. I am a assistant research scientist at the University of Maryland, Baltimore County, working at NASA Goddard. And thank you very much for being here this morning. I know it is 8:30 and it is early and it is the third day, I believe, in a row. But as a special surprise, we have a projector working, so you can so been maybe not so much of a fun time, but we sincerely appreciate you. And now I get to show pretty pictures. I tried to show as many pretty pictures in my presentations as possible because, yes. Okay, so I'll go ahead and talk about the future of supernova cosmology with the Nancy Grace Roman Space Telescope. And I do want to point out that a lot of what I'm going to be talking about today are from members of the project infrastructure team that I'm a part of. And this is Zach Ranney, who's a student who worked with Dan Skolnick over at Duke, but he's at Virginia, Rick Kessler at Chicago, Dylan Brown at Boston, Stefano, I don't know if they're in the room, but obviously they're here at Space Telescope, Dan Skolnick and David Rubin. And David Rubin is in Hawaii. So let's get cracking. Okay, so my talk motivation is this. Roman, as we all know, is going to be absolutely amazing. It's going to conduct this monumental time domain experiment with a focus, well, what I'm interested in focus, on Type 1A supernovae. And these supernovae are going to be collected. There's going to be a huge sample. They're going to be some of the farthest redshift. They're going to be very well defined. We're going to get a great cosmology sample from them. And Rome's going to have a significant, because of this, it's going to have a significant impact on our understanding of dark energy and the universe. Part of this, however, means that we really need to understand our systematics. That's what it's work is about, understanding calibration, understanding flux. So we really need to understand our systematics really well to make sure we're taking full advantage of this amazing mission. So I promised some pretty pictures. Quite pretty. Okay, so first off, I wanted to give like a little bit of an introduction to Roman. I'm sure most people here know about Roman, but if you don't, I'm just going to give a very brief overview. So Roman is NASA's next flagship mission, I believe, due to launch October 2026. Please correct me if I'm wrong on that statement. Thank you very much. And it's going to have the main workhorse of this amazing facility that I'm interested in is the wide field instrument. And this is a near infrared survey mission. And it has a filter wheel with 11 slots, 8 are science imaging filters, one's a prism. You've got your blank for your darks and your flats. And it has these 18, so these are 18 H4RG chips arranged into the 6x3 array, as you can see here. And the combined field of view, which is what makes Roman even more special, is this 0.281 square degrees, which, to be frank, is massive. When I say massive, I always like showing this slide because it's pretty and I thought it's pretty pictures. So this is the pillars of creation with Hubble, and then this is an impression of the field of view that Roman is going to be able to cover with one pointing. And I have the wrong date there, I apologize. Okay, so this huge field of view. So Roman is classified as a stage 4 dark energy mission. So I'm going to go a bit into what that means and why we are therefore interested in making sure this is extremely well calibrated. Oh, there we go. So we think that we live in this lambda CDM universe and that it is made up of, a lot of dark matter, a lot of dark energy. And however, we know that there are lots of different kinds of cosmological models, and we use evidence from cosmological probes like GMB, supernovae, quasars, BAO, to determine which model is most likely. And one equation that we tend to rely on to distinguish between things, and now it's showing, the equation of state, which is given here. And so you have dark energy pressure, dark energy density, equation of state, scale factor of the universe, etc., etc. Now, this is one of the most recent results from the DESI collaboration, the 2024 paper. And this here is the one way we like to show, how we're constraining different cosmological models, how well we're understanding the universe that we live in, assuming that we're having this cosmological constant universe of W0 minus 1 and WA being 0, is to do these cool little contour plots here. So WA, W0. And what we're really trying to do is, instead of making this elliptical, we're trying to squeeze it down into a point to really understand exactly where we're living, what kind of universe we're in, and we're trying to get the uncertainties beat down, essentially. Now, I took the results from the DESI, BAO, CMB, and Pantheon Plus result from this paper, and you can see that these values are kind of maybe off, well, not off, but different from potentially, W0 being minus 1, WA being 0. And I believe that blue are 2 sigma results. The reason why I'm showing this is it's really hard. And we need a lot of data, and we need to, again, really understand our systematics. Another reason why I'm showing this plot is because there's this thing which is called the Dark Energy Task Force Figure of Merit. Do people know what that means here? We have, okay, great. So we have, this is defined as the inverse area of the 95% confidence contour in the W0 WA plane. And a long while ago, well, 2016, there was the definition of a stage 2 dark energy mission should have this figure of merit of 32.6. And that for something to be classified as a state-of-the-art stage 4 mission, this number needs to be increased by a factor of 10. And what that really means is actually decreasing your errors in W0 WA by a factor of 3. And as we know, supernova 1A from plots have been shown beforehand, and knowledge of supernova 1A are extremely important cosmological probes, but we've got to understand the systematics. Okay, so I talked particularly about what is known as the high latitude time domain survey. This is the survey that Roman's going to conduct time domain wise to focus a bit on type 1A supernova. And so I'm going to talk about that here. So In case you didn't know, Roman has 4 core community surveys being planned, and the focus of this particular one, as I said, is time domain science. Key objective of the survey is to collect, again, one of the largest samples of cosmological worthy type 1a supernovae and improve our knowledge of dark energy. The survey itself is expected to occur over a 2-year period, probably total observing time around about 6 months. We'll use some combination of imaging and spectroscopy. Cadence and filters and things like that are still up for debate, but this is kind of like a rough outline of a design. When we talk about Roman, what we're really talking about is kind of expanding our knowledge in this direction in redshift. So unfortunately, this is not a complete plot, as you can see, it's only got some of the surveys listed here. I tried to get an updated version, but didn't have enough time. But this is some of the information that we currently have about the space of supernovae occupying in redshift. And at greater than redshift of 2, we only have a few supernovae, handful or so, occupying the area. Roman is going to significantly increase that. It's going to be thousands of supernovae detected at these higher redshifts. And as I said, the optimization survey right now is ongoing. And I know there's probably a lot of information here, but it's just showing some things of like, where are we going to put the survey? What is the cadence going to be? The depth, et cetera, et cetera, et cetera. And the reason also why I'm talking about this is because of the fact that systematics play a part in designing the survey. So depending on your knowledge of, for instance, 0 points, nonlinearity, all those different things, it can affect the best survey strategy that you might want to pick for optimizing, getting a good supernova 1A sample. And so how have we tried to understand this? Well, simulations. We have used in the past SNANA, but there are other tools as well. SNANA is a supernova analysis package to essentially take a recipe for supernovae, our understanding of them, take a recipe for the Roman Space Telescope, our understanding of that, put in different scheduling constraints, add in a bunch of other information about, supernova physics, color structure, etc., and simulate light curves and spectra. Oh, and one got mixed there, but mix it all up, add in our systematics, get out that contour plot that we're interested in and that figure of merit value. This is a very quick overview. I can give more information at a later point, but I just wanted to give an outline of some of the things we do to try and simulate survey designs and take into account these different systematics and effects. Okay, so past attempts at understanding systematics. So a long while ago, in 2018, the SIT, as it was known before the PIT, there was a SIT that was different, but had a focus on, supernova science with Roman, tried to create some of the first realistic simulations of what was then known as W-first supernova survey, and now the Roman high latitude time domain survey, because it really is focusing on time domain science in the near infrared now. And we essentially simulated these light curves and spectra, propagated statistical and systematic uncertainties, and provided some input for some investigations. And I've grayed out some things here because I'm not going to talk about them in this talk, but essentially things that we included were what we called the wavelength-dependent calibration. So constrained dark energy, we need to know the supernova brightness accurately from low to high redshifts. And so depending on the redshift of the supernova, we see the peak in different filters, which means we need to know how well calibrated each filter is with respect to the others. So for this systematic, we included this 5 millimag per 7,000 angstroms from Hubble. We also included some form of nonlinearity. We took that from the Rees et al. 2010 paper, which had this 1% per dex over a range of 4 dex. And we included some 0-point offsets, and we took 5 millimag for each filter. So this is kind of some of the initial assumptions that we made when we were trying to do these surveys. We had a bunch more, but essentially this is what we put in 2018. And what we did, as I said, we used the tools I talked about earlier to propagate these through survey designs. This is just an imaging focused one. And we looked at the effect that each systematic had on the figure of merit. So what I'm showing here, this is if you have up here what we had the optimistic. So we took some slightly better values, hoping that by now we would have improved our knowledge of these systematics, versus the current understanding, or what we called the pessimistic at the time, and tried to show how each one of these affected, the performance of a given survey strategy. So one thing that I want to briefly touch on and go over is nonlinearity. And I want to kind of talk about detectors and give kind of just this overview of, let's talk about these detectors. These Roman detectors are the mercury, cadmium, tellurium IR detectors. They accumulate signal, it's read off at different times. For the Roman, the reads are about 3 seconds apart, and the effective signal is measured by the count rate. So how fast counts increase with time. It's not like CCDs. And essentially what you would expect is constant illumination. With constant illumination, the count should increase linearly with time, but they don't. So we think of it in two flavors. There's classical nonlinearity, which is the increase in detector counts is not linear at high light levels. So basically, as the signal accumulates, the effective capacitance of the pixel changes. So even if the charge increases linearly, the measured voltage does not. And the effect becomes more prominent at higher detector counts, so 20K. There's also, but it's also present at lower counts as well. And at some point, you obviously hit saturation. So this is very important to correct for because it's critical to valid measurements of the count rate. So, your supernovae, so understanding the count of the signal of the supernova. Typically, it's corrected for the polynomial. And the assumption is that this polynomial applies to all data taken with that pixel. In our 2018 analysis, we didn't actually include this. We just assumed, it's be correct and it's all going to be fine. I know. I know. We thought about the count rate nonlinearity. We didn't think about this so much. I understand. Then count rate dependent nonlinearity. This is a much more subtle effect. So this appears after classical nonlinearity is corrected for. So classical depends on total accumulated, count rate, it's count rate. CNL is small, can result in a few thousandths of a magnitude effect in the photometry, which for 2022 and what we're talking about when we're going out to these high measures is really, really important. So we obviously back in 2018 we used the results from the Rees 2010 paper for nonlinearity, which is again just 1% over a range of 4 mag, and we also knew potentially that it may be wavelength dependent. There was, we don't really understand too much. The physics is not really well understood. One of the things that we did out in 2001, so Susanna is in the room who led this paper, hello, was we started to think about, okay, well, how can we really correct for these effects? What can we do? And obviously a lot of people from the community, so we have the calibration working group and project, lots of people in the community came together to think about how to account for this. What could we do on board? We needed this calibration, what at the time was known as a relative calibration system, is now the simplified, I believe, relative calibration system. And so what could we do to really understand this effect? So there came up with two designs. There's this direct illumination, so it provides light on every pixel of the focal plane for each filter spanning a flux range equivalent to that between a 50th mag and a 20th mag supernova. And with this method, CRNL is determined by the ratios of any two illuminated levels for each filter. And then there's lamp on, lamp off, which provides this pedestal light level to the image on an astrophysical scene, essentially, and it's compared to an image of the same scene with the pedestal lamp off, so lamp on, lamp off. The measurement uses simultaneous imaging of many sources over multiple flux levels to determine CRNL. So there's different methods. And so this work by Susanna, Dave Rubin, and myself essentially looked at, so the black line here was, the figure of merit that you want to try to reach. This is within some percentage threshold, and the different things that you might need to do using different combination of these things and the different filters to make sure that you were going to hit the figure of merit and what wouldn't really work. If you didn't account for it all, how significant that impact would be on the figure of merit itself. And it was deemed that it would be something like 50% it would hit it by. So that's obviously very significant. And it clearly indicated that we needed this very robust, relative calibration system. There's also lots and lots of work that people went into writing many, many reports and lots of information. For those of you who contributed to these reports, thank you so much for how to come up with a good calibration plan and what specific requirements we needed to meet. So all of this was, what did we do in the past? And now where are we at and what is currently ongoing? And I just wanted to give a brief discussion about that. So going to start with talking about the Supernova 1A cosmology project infrastructure. So back in 2023, I believe, my colleagues and I formed a team to develop infrastructure for Supernova 1A cosmology. We submitted our ROSA proposal and were successful. And in this proposal, we obviously knew that calibration would be extremely important and vital for the success of achieving this objective of making Supernova 1A very well calibrated. And we have these deliverables which are listed here, which are ambitious, but hopefully not too ambitious. And one of the things that will stay in all of this is there needs to be thorough study of dependencies between uncertainties and how these propagate through. And so this is something, so as well as understanding each one of these individually, understanding them all together is extremely important. So this week, there have been talks by Eric, there have been posters by Ami, there's been posters by other people in the room about all the work that the SRCS team have been doing and the projects have been doing. There's been a huge effort to really understand these instruments, and for all of your hard work, thank you so much. Some of the tests that I've been particularly interested in, our team has been particularly interested in, is this combinatorial flux addition, so CFA. And this is essentially where you have these pair of LEDs emitting light from a given band, and it's assumed that light from both LEDs individually should surmise to the light of those combined. If the response to the detector deviates from, this linear response, then that indicates that there is obviously, non-linearity. And the full tests, and please again correct me if I'm wrong, I think it was something like 53 tests, if that's right, for different combinations of LED settings. So LED 1 on, for example, LED 2 on, both off, etc. And then other tests that we were interested in is measuring the filter bandpass edges and determining shifts. Eric, thank you very much, gave a wonderful talk about that remotely yesterday. And one thing I think that everyone's learned is Roman is really complicated. It's really complicated, and there's variance in systematic parameters like across each detector and across the field in general. So we need to spend a lot of work trying to understand these data. And so fortunately, we have some amazing people on the team who have spent some time trying to understand some of the TVAC data that we've been able to access. So this is work that's been done by Zach Rennie and Dan Skolnick and Stefano. And essentially in this situation, what we've done is on the left, and I'm glad that we have this large projector here, on the left, we have essentially looking at specific pixel on a certain activity that's happening and going from one map to the next. You have your, say, test LED 1 and LED 2, each activity is unique, and then you have this cumulative up the ramp total counts. And, this should be linear, but obviously this is a residual and it's not. So what you can do is you can try to do this per pixel correction, this polynomial, try and fit it to the data, and then this is the residual here. Now, you can also try and do this in more of a global way with looking at, the average thank you very much, per 1,000 pixels. And that was what's done here on the right that's being shown. So this is looking at an average over 1,000 pixels without correction and with the correction. Additionally, one thing that Zach found when he was doing all of this work, that actually maybe the path forward with this isn't doing two separate ways for filling the classical and then the count rate, but actually doing things kind of together. And so instead of optimizing for classical, like I said, correction, and then seeing how it affects the RNL, do the model for both simultaneously. And so, you take the predicted measure values, you optimize the model so that measure values can be turned into ideal values. And I know this is extremely preliminary. Initial sample of such a method is shown here. And this is only on a small subset of data. I want to be very clear about that. And the optimization was stopped after a limited number of iterations. And the work is very much in progress. We need to do it over all the activities and do it over the broader range. But what he found was of order of 0.5% over the 4.5 dex. And the next step, as we said, to do is more complete analysis. Now, yesterday, I went to go look at all the posters, and I said there are some really, really interesting posters here. And this is a preliminary result that was showed in Ami Troy's poster. And if I'm misrepresenting anything here, Ami, please let me know. But essentially, what they found for the CRNL, they got this 0.3% value over this 4.5 dex, as shown here. And this is for band 2, which I believe is Z, or what I call the Z band. And again, thank you to everybody here for your work on this. Okay, so we've talked a bit about some of the stuff that we initially started looking to. So how about that into SNANA and propagate through onto a particular survey design? So I have these things that are listed here. So we have the wavelength dependent calibration. This is the same as beforehand. Then we have this transmission shift, which is a new thing that we've included, and we've assumed this 5 millimag. Again, see Eric's talk from yesterday. We have a 0 point offset, and this is really important, but we have currently 5 millimag until further investigation. Classical nonlinearity, we didn't include that in 2018. We need to, so we need to work more on this. CRNL, what we actually did was assume this, 0.5% over 4.5 dex. And I'm going to talk more about that in another slide, so please hang on for that. And then also, obviously, cross-survey calibration. This is really important when we think about getting our lower redshift sample from surveys such as LSST, for example. So talking about forecasting CRNL. So Roman nonlinearity uncertainty measurement, requirement is 0.14% over 4.5 dex. In the event that these errors are uncorrelated between pixels, this will average out as negligible, essentially, in the noise of the signal cosmology. However, correlated errors between the pixels will propagate through. So work by Dylan Brout, Kessler, and Stefano was used to do this preliminary assumption that the correlated residual sources of error make up about a third of the total uncertainty. So essentially, this 0.05 over the 4.5 I mentioned earlier. So this is just showing a plot of the distance nonlinearity versus the nominal. Please note here that this is because we've not included the low redshift nonlinearity is ignored here. This is a preliminary result again from Armin Choi's paper, which indicated that the value was around, I mean, you can see it here and make an estimate, but this was their uncertainty. So it's 0.06869 essentially value as shown here. So a test case, and I am going to say before I show this plot, really is a test case, very preliminary. We literally did this like 2 days ago or a day ago, just trying to understand how things actually work. So, as I said, the core community survey team is determining what kind of survey they might have in the future. This is just an example. Please keep that in mind. It's just an example of different design they've been looking at. So 50% prism time, 85% imaging. What we've done, there are a bunch of different systematics here, but what we've done is included the ones that we talked about beforehand. So the CRNL, filter shift, and then the redshifts. And what we're seeing is if the CRNL is really as small as we expect it to be, or we hope it to be, this is a success-orientated plot. I'm going to be very clear about that. Its contribution might be very negligible. But what's really going to be a significant contributor will be the 0 point uncertainty. And with that, my last part is saying we have lots of work to do, not only from understanding things like the nonlinearity and the 0 points and all those other things, but also understanding the supernova physics as well. And we have a lot more work to do. That's pretty much what I have to say. Thank you very much for your time.
Questions for Rebecca?
So I normally think of 0 points as absolute calibration, but the supernova community often only cares about relative redshift. So I'm confused why 0 point is the biggest contributor to the uncertainty.
So Susanna, maybe you want to take this one because I talked to you about this yesterday with the standard stars and things like that. But yeah, I'm going to hand this over to Susanna.
So do you think of 0 points being the absolute? Really, I don't want to. You want to know.
Yeah.
There are a lot of people in this room who can answer. Bottom line is that 0 points means different things to different communities. And if you're talking about the supernovae, what's really important is the absolute color. And so
Your 0 point and you're uncertain on that pop, but you don't know your color very well.
right. So you need to know what's happening in each filter. So you need your standard starts to give you that response. I mean, it's not the absolute flux of, exactly how many watts. It's the relative value. But you have to get that right.
Oh.
Other people may have different interpretations.
I think of it as color. essentially.
Yeah, that's right.
Let's take a question from Carl.
So just to, I guess I'm still struggling trying to understand how you do getting absolute color right without doing absolute. How do you know you got your color right if you haven't got your absolute flux right? I haven't figured out the mechanics of actually, do we have any absolute color sources we know any better than we know their absolute flux?
It's a good question. I don't think we do, really.
All right, maybe I'm just being hopelessly optimistic, but I mean, if we don't know how bright a star, if we're off by 5% how bright the star is, that's one thing. That's a mistake I could see. But I think going from J to H or H to K, the uncertainties would be far, far smaller because most everything is just up or down, right? The whole thing goes up or down.
Statistically, you're correct, but how would we test that?
I mean, the other issue is it's the same bloody detector, right? I think most of the problems in absolute are the detector. So we're using the same detector with different filters.
You're making theoretical arguments at this point.
I am. I'm not answering how to test it, but
I saw Ralph's hand. I think maybe he wants to weigh in, so.
Answer Carl's question.
Yeah,
It's got a fairly simple answer.
Excellent.
In that if you color is determined entirely by the slope of the three primary white dwarf flux distributions, which is entirely independent of their normalization. So and the color is the only thing that matters. Now, the slope of the white dwarf SEDs determine the color, and that's the only thing that's important. Absolute normalization has an independent exercise. There's no relation to the accuracy of the cosmological analysis.
Thank you.
Anyone else?
So we have a question online.
Oh, yeah, go ahead, Steve.
Let's tackle that. Busy is asking, what is the mode of data release and the arc second per pixel resolution of the telescope?
So each pixel is 0.11 arc seconds. And what do you mean by mode of data release? Do you mean?
I assume how they're going to release the observations, like how are they made public?
You mean Roman in general, or what
I assume
we're
that.
doing? There are people from the Roman project in there who might prefer to answer that
It's
question.
going to be released immediately.
Yeah, it's all public, not proprietary. So,
Okay. Okay, Busy, let us know if that answers your question. If not, we can follow up.
Surveys.
Pardon?
For the surveys, the data are public, but there are also the geos.
Right, but I believe that all data is not proprietary, regardless. Yeah.
Okay, let's take one more question, please.
You didn't mention anything about persistence.
So persistence, I briefly touched upon something the Army had in her poster with regards to persistence and CRNL and how that might need to be, the potential degeneracies, I guess, in that and how that might need to approach the same. Persistence, we had a discussion about that yesterday a little bit, and we know that it will be an issue, and I believe that the project and Space Telescope are going to flag persistence. As far as I'm aware, there is no plan to model or correct for it, but I can imagine that it being an issue on some percentage level. Yes, but as we talked yesterday with the Euclid people, that maybe it won't be too bad. But I'm not going to say more than that. But there are others in the room who might want to talk about that, and I'm looking at you.
You briefly mentioned correlation between pixels.
Right.
Can you describe a bit more the test that you have done and?
So the effect that you will see, when you're talking about it with regards to the supernova, is the signal from the supernova, like you're looking at the PSF and everything. So but the CRNL is we're looking at per pixel. So you need to understand how it affects things as a whole, not just on the per pixel level. So we have to do the. Sorry.
What test have you done to determine it?
So we made assumptions. We didn't run tests to thoroughly go through it. We made an assumption based on advice with.
The test that can be done pretty easily is just make the cross correlation between on the plasma.
Right.
And you will see, and sometimes you can see very surprising effects.
Okay.
Another one is just eliminate a single pixel and see what's the output that you need a specific.
We have a lot more work to do. As I said, we only just really started looking into this in the last few weeks. And
Okay, last question, I think, is we want to schedule. No worries. Could you pass that back, please?
Just to follow up on that, this is for my curiosity. Are you modeling this like with the H4RGs, like each pixel is its own thing, but when you model this, are you doing a whole region at once, or are you measuring a CRNL per pixel
so like I said, we
individually?
haven't really modeled anything right now. We've just made assumptions based off of some information that we've had. So we made that 1/3 assumption about how it correlates
Okay.
through, but that's pretty much it.
But when you've measured it, you've shown some
Oh, you mean
yeah.
through, you mean this one?
No, or
In the previous
you've
ones here.
this one here and all, yeah. Is this a per pixel modeling, or
So
you
this
just
was looking-
averaging a whole bunch
So
together?
there was one which we looked at it averagely and like in a global way, but I believe this was per pixel. And I have some more information on this. I can show you in a separate slide, but I wanted to take some of the stuff out
I'll
of it. But
try
yeah.
to catch up with you.
Thank you very much, everybody.
Well, let's thank Rebecca again, please.
Is going to be Greg Snow, and he's going to talk about some of my favorite calibrators who trouble with K-giants, the challenging class of mid-infrared stars.
Where am I? Yeah, but there we go. Oh, crap.
Switcher.
Hang on. Okay. Tell me.
So yeah,
It's beginning to swap the presentation.
yeah. No, it wasn't, but it's not on this. Do we mirror the display or?
Right, so go to
Okay.
Where do you want to go?
view. So when you did this, enter full screen.
There we go.
No, okay. Kevin,
It's a PDF.
I
I can go ahead and start. Y'all figure it out.
did, yes. You do to extended display, not mirror display, and it's a button on the touchpad.
can you comment?
I can indeed.
Yeah.
So I'm gonna go ahead and start. So I'm gonna talk about 40 years of spectrophotometric calibration history in, well, it was 15 minutes. It might be less now. So the one thing I want you to take away from this is, since I'm going to talk about the mid-infrared, you can thank the Lord that Roman is a near-infrared mission. All right, let's see. All right, so just real quickly, I'm going to kind of cover 3 missions. These are the 3 infrared space telescopes that we've launched that have spectroscopic capability, like with a dedicated spectrometer up to JWST. So IRAS, which launched 41 years ago, had a low resolution spectrometer, the LRS, the original LRS. I'm the mode lead for the LRS now, but that would be LRS Mark II. The short wavelength spectrometer flew on ISO a while ago. I don't know what's bouncing there. It's kind of cute. And then the infrared spectrograph, which was one of the 3 instruments on the Spitzer Space Telescope. Too far away. Talk to me. Okay, so this is just a comparison of the spectral class of stars. In one plot, that's the Yale Bright Star Catalog. And you can see that the majority of the stars are either A dwarfs or K giants. And if you go to the near infrared, the 2 micron sky survey, which is what, 55 years old now? Almost everything that's bright in the sky is either a K giant or an M giant. And so the bottom line is that in the infrared sky, K giants dominate. They're everywhere. There's plentiful. And this is the reason that they became a standard. Now I have to run back here. All right. And so here's a typical mid-infrared spectrum of a K giant. And if you just plot in flux density, F of nu units, You can see there's a couple of notches in the spectrum, but those don't look too exciting. But the reason we like to plot in Rayleigh-Jeans units is because basically Rayleigh-Jeans units, if there's any issues in your data, you will see them in Rayleigh-Jeans units. In this case, the first thing you see is that there's a bunch of pretty deep molecular absorption bands. The one I'll be most interested in is the SIO fundamental at 8 microns. But you can also see in the spectrum, this is an SWS spectrum from ISO, and you can see that the signal to noise gets pretty unimpressive at the longest wavelengths. And if you look over here just in flux density, you can't see squat. And so this is really a nice way to plot things. So here's the calibration equation, my version of it. Ralph had a different version. Looks very simple, but it is not. So what you're after is S sub T, that's the true spectrum of your science target. And what you observe is S sub O, that's the observed spectrum of your science target. C sub O would be the calibrator, the observed spectrum of the calibrator. So you take that ratio, and then you multiply back through by the assumed true spectrum of your calibrator, which these days would come from CalSpec. Except CalSpec has wisely avoided K-giants. So the bottom line is that, so everything here is a vector, everything's a function of wavelength. And the issue is that if you make any mistake in the assumed calibrator truth spectrum, that will propagate into your entire database. And yes, that has happened a few times. So here's IRS, here's the LRS spectrum of alpha tau, Aldebaran, one of our primary standards because it's like, what, 1,000 Janskys at 12 microns? Pretty bright. 300, it's anyway, can't remember offhand. But the bottom line is that we had assumed in the 80s, we didn't realize there were any molecular bands in these spectra, so we just assumed that they basically fell off as a Rayleigh-Jeans tail. And that is not the case. You've already seen what that deep molecular band at 8 microns, and we assumed it wasn't there. And so you can see here in this plot, there's this is a classic plot from the early 90s, which means it's hard to read. But the thickest dashed line is like it's an assumed 10,000 K black body, and that was what was assumed. This is the calibrated spectrum of alpha tau with that assumption. And then what happened is that people began to realize that this had introduced a 15% emission artifact in the spectrum of everything in the 5,000 spectrum in this database. When I say people, actually, I learned recently it was Kevin Volk, our own Kevin Volk, that figured this out. And so he was working with Martin Cohen at the time. Kevin went back to Calgary. Martin Cohen kept looking at this, and he came up with a solution. This is a plot of, I made this plot more recently to kind of show this, but there's Vega on top, there's Sirius in blue, and you can see there's this ridiculous 15%, 12% artifact. Well, it's like a 15% artifact here. And then you can see there's a 10 to the 4th black body underneath. So that propagated to everything. Martin Cohen set about fixing it. The solution that he used was, we'll take the A dwarfs, Vega and Sirius, we'll use them to calibrate what the real spectrum of a K-giant should be, and then we'll use those K-giants to calibrate everything else. Where what we'll do is we'll actually use everything to calibrate everything else. So he built this network of, he called them composite spectra. We refer to them as spectral templates. The idea was that beta gem would be our classic K0, and then every K0 giant should look like that. I mean, you can see that there's a few things here. You can see that the absorption bands, the CO at 5 microns, the SIO at 8 microns is getting deeper as you go to later spectral classes and lower effective temperatures. But the idea was Vega calibrated Arcturus, Sirius calibrated Aldebaran, and those 4, he just kept propagating by ratio to calibrate everything else. And he did it in pieces. So he used Pickles spectra, if I remember right. He used data from the Kuiper Airborne Observatory, everything he could get in ratio. Okay, so we fixed that. He basically created a set of corrections. The LRS database is all fixed. So now ISO launches. Their primary standard was gamma draw. Basically, we just used alpha tau as I wasn't involved in the calibration, but that's what they did. But they changed that because what happens is if you're using these spectral templates, I should go back, see if I can. Which way am I going here? There we go. Yep.
you can see that like in the blue spectrum for alpha boo, you see all this noise at 15 microns. That's just noise in one of the ratios. And that's now going to propagate into your database. And that was not a good thing. And so the ISO mission decided that they were going to switch to using synthetic spectra. And they test those spectra pretty thoroughly at short wavelengths. So here's a spectrum of gamma draw. There's the synthetic spectrum, and you can see that it's matching the detailed line structure in the band really well at 2.4 microns. It turns out, if you look at these figures on the left, that they didn't account for the discontinuity between spectral segments, as they thought they had a match at the 8 micron SIO feature. And you'll note they're not plotting in Rayleigh-Jeans units. So if you turn around and plot these up in Rayleigh-Jeans units, you can see that they had basically repeated the mistake of the LRS on IRAS, and they propagated molecular band mismatches into the database. I should add that they did this for what they thought was the last pipeline release, OLP 10.0, and so we had it to test. By the way, Kathleen Kramer, who's also spotted this one, and so we wrote this up, wrote back to the people in Europe, and said they need to fix this. They were a little slow to respond, and so they did finally fix it in 10.1. So they basically went through and fixed everything. And you can see here the nature of these errors. Okay, so that brings us to Spitzer, and what I have here on the left are our two main K-giants. So we didn't realize quite yet, all of this stuff happened with ISO right as we were planning for Spitzer. So we didn't make this adjustment. We just forged ahead with the K-giants. We figured that we would just use the Cohen templates. And you can see, though, that in purple up here, you can see HR648. That's the Cohen template, and all those wiggles up and down, that's all noise. So we quickly realized that was bad. And so we smoothed the spectra to get rid of the fixed pattern noise. And that was great for getting rid of the fixed pattern noise. But if you notice at 14 to 18 microns, I have this marked, these OH absorption bands. I smoothed those out too. So I introduced an artifact to the IRS database because I added little OH wiggles and all the other data, in stars and galaxies that shouldn't have them. The galaxies people brought that to my attention pretty quick, and so we had to go back and fix that more properly. So you can see that, you basically, it's an iterative process calibrating. You just try to make each mistake smaller than the one before. And I should add, so basically in the end, the calibration dropped several percent as we shifted from the Cohen templates, which are calibrated to IRAS, to the MIPS 24 calibration, which George Ricci had published at that point. So everything moves down, and then our final truth spectra are in blue. Oops, too far again. And we basically just made these the same way Cohen did. We took our A dwarfs, and then we calibrated the K-giants in ratio. We went through in detail, cleaned everything up to get rid of residuals where we didn't match the atomic lines in the A dwarfs. Anyway, I have backup slides if people really care about the sausage making. And we published this all in 2015. So there's a pretty good atlas there of stuff. And then somebody else expressed an interest in K-giants. The problem is all these spectra stop at 5 microns. So they're no help at 2.5. All right. So the deal here is this is a plot of the equivalent width of the silicon monoxide band at 8 microns as a function of B minus V color. So basically, the early K stars are over here on the left, the K5s are over on the right, and you can see that this sort of plots how that SIO band gets stronger. And this also, the green triangles are basically extracting the equivalent width of that band from the synthetic spectra that were the same family as what was used for ISO. Those were provided to Spitzer as well. And you can see that the synthetic spectra are consistently weak. The bands they're producing aren't right. And so from this, we can draw two conclusions. We really don't have a way to generate truth spectra a priori for these K-giants. Also, you'll notice that there's a great deal of scatter at any given B minus V. So you take the same 2 stars, both K-giants, same luminosity class, same temperature, and there's a range of possible molecular band depths. So, and I should have added as a reference for can't use K-giants as standard, that would be Gordon and Bolin private communication, because I remember the conversation we had at a AAS meeting where we had adjacent posters and Carl said, you know what, we're going to fire the K-giants. And at the time I was not happy because I was really thought I'd have this problem solved, but I think this was the right thing to do. And so now we have A dwarfs, solar analogs, and white dwarfs, and the K-giants are not to be heard from. So I put together an observing proposal to look at the 4 K-giants that we looked at the most with the IRS. And I actually had 2 motivations to do this. Carl's on the team, Kathleen's on the team, Aka and a few other people. Bernard Ehringer and Jan Kami are the people that provide us with the synthetic spectrum. So first of all, why don't the synthetic spectra work? What's wrong with the models? Probably what's happening is they've got the molecular band absorbing layer at longer wavelengths too close to the star. And so the idea is that with the MRS on JDBST, we can break apart the bands. We've got the lines, so we can fit the lines and we can work out what the temperature and pressure ought to be. So we can test the models to figure out what went wrong and maybe we can fix them. You might hear a small tinge of hope when I say that. Maybe we can model these things. I'm not so sure, but at least we can figure out what went wrong. But the other thing we can do is, because we're now observing the 4 best observed stars with the IRS on Spitzer with the MRS, we can compare the calibrations. And that's what I have here. So this is the latest, greatest calibration that came out at the end of this summer. And so this is just the ratio. I've taken the MRS data and I have binned them down to the IRS grid and then just taken the ratio. And so this is kind of like the happy news. In ratio, if you look at the 4K giants, we're basically within 1%. On average, we're about 1% off, but that's pretty close. You'll notice that in channel 4, I can't make any guarantees. Channel 4 has still been a problem child for the MRS. And the calibration there's not so good. We also have 3 A dwarfs in common between the 2 spectrometers. And I'll just say that you'll notice the spectra for channels 1 through 3 are quite flat. There's a bit of discrepancy in the overall ratio. That is probably due to nonlinearities in the calibration of the IRS. That's my guess. I don't know that, but I don't think there's any reason why the MRS would be responsible for that. All right, and this is the same plot in different ways on the right. That kind of shows the same 7 stars, and these give you harder numbers. The bottom line is that we're now 1%, 1.2% different on average. And this is actually the older calibration that we were using up until this summer. You can see that it's a major improvement. We've removed 4% of mismatch between the calibrations. And that's because we're relying on 10 lac, the O star before. All right, and what else? I think I've got, oh yeah, I just wanted to add, this is the OH band structure at longer wavelengths. And I just want to say it's the same problem. This is what they look like for the IRS. There's 8 of them here, and I've got those plotted. I also have the synthetic spectra results. You can see the OH is underestimated as well. And then my last slide is a comparison of the IRS data and then the MRS data for the same bands. I apologize, the horizontal axes are a little different, but you can see that we can see the gory details of the line structure now. So all we have to do is fit it. That's it. Thank you.
Questions for Greg?
I've got to get out of it.
Oh, that's
After now.
I don't know, should we just start shouting at the ceiling?
Yeah.
For it.
I was surprised I didn't hear anything about the metallicity of the K-giants and how much of the spread in there could be explained just by metallicity, because I know like Arcturus is a really metal poor compared to some of those other giants that you had.
That's a pretty likely possibility. We haven't tested for that.
So somewhere between a question and a comment, for the sun, the reason that the CO bands are too weak in the models is because there's this 3-dimensional structure and the CO is mostly above the sunspots. When you go to K stars,
do we really understand how much of this is due to just the plain parallel atmosphere assumption of the stellar atmospheres versus you'd have more complex structure in 2, maybe 3 dimensions, and it's very hard to deal with that.
So we're approaching this in 2 ways. So Jan is making, you know, he just gives me a cubic centimeter of gas at a given pressure and temperature. And then Bernard Ehringer is making models. And his team is involved in, they're adding convection cells and spots to their, well, not spot, convection cells to their models. And so, yeah, that's kind of the thinking that we can eventually get to there. At that point, I'll turn everything we know over to the modelers in Europe, and then we'll hear back from them.
Anybody online?
Time to get out of the way.
Questions, but maybe we'll
We'll go offline.
We'll go offline.
Yeah.
Okay, let's thank Greg then.
Next up, Daniel Koosters is going to talk about NIST traceable optical flux calibration with Scala.
Let me just set the timer then.
Thank you. I will start with motivating why we need improved calibration for cosmology. Afterwards, I will introduce you to the SNF's integral field spectrograph and conclude with the SNF's calibration apparatus Scala. So what we are doing is we look at supernova of type 1a. They are standardizable candles. We can measure the luminosity distance, the redshift. If we do that over a wide range of redshift, we can fit for cosmological parameters like the properties of dark energy. Our standard model is a cosmological constant. So up here, however, recent compilations measurements from baryon acoustic oscillation and cosmic microwave background together with supernova 1a show attention to the cosmological constant of bigger than 2 sigma. Now, we have heard calibration can shift the ellipses. We want to make the ellipses smaller. We define the figure of merit as the inverse of the area of that ellipse. Okay, if we say nowadays we're at a calibration uncertainty of the order 1% and normalize our figure of merit to 1, how much better can we get? Our plan was to get a calibration of the stars relative to Carlsberg to of the order 0.5%. So we would end up here and would shrink the error ellipses by at least 50%. Now, how can we do that? We first need an instrument which we can calibrate with enough precision, and then we need to put it onto a system. Our instrument, that's the Supernova Integral Field Spectrograph. It was mounted to the University Hawaii telescope in 2004, and it's permanently on. It has a field of view of 6.4 times 6.4 arc seconds, sampled by 15 by 15 spexels. Each spexel is giving us a spectrum between 320 nanometers and 1 micron with a resolution of 3 angstrom. Observing standard stars with the system, we can measure the extinction using Beers-Lambert's law and then correct our data. And doing so, we have obtained spectrophotometric light curves for more than 300 supernova 1a. Now, we have this instrument since 2004. David Rubin has looked at the standard star observations since then, has done a calibration. What we are left with is an RMS color in the red, in the red here, of 1.1 millimag per 1,000 angstrom, and in the blue of something like 4 millimags. So that's precise enough for our 0.5% goal. We can put SNFs precisely on a system. This system here is the Carlsberg system. So we tie SNFs against the model atmospheres of the white dwarfs. Now we want to do something different. We want to tie it against the SI system. For this purpose, we have built Scala. The idea is we put it against a standard in the lab, which we can test, which we can, worst case, falsify. So how do we do that? We have calibrated for the diodes. In between our light source and the telescope, we measure how much flux we are emitting. We have the telescope With the detector, we see how much we get through. We can measure the transmission. To do so, because the detectors are broadband, we need a monochromatic wavelength tunable source. We would like to have an artificial star. However, that's difficult. We make an artificial planet. And we want to have as much collecting area as possible, so we shine 18 parallel beams into the telescope. There are alternative designs to do that. A flat field, we have heard, is producing a lot of scattered light. We could use a distant source. However, we have a 2.2 meter telescope, so distance would mean at least 300 kilometers. That's a bit difficult. We do not want to have defocus or a smaller telescope, so that's not a solution. So what we do is having a local source with a collimator to place the source into the far field. Now, how does Scala look like? That's the whole system with the UH-88. How it looks now. We are working on that since quite a while. We started in 2012. We installed the first version in 2014. We took data. The results you can see in the PhD thesis of Simona Lombardo. We had severe systematics. We need to characterize a lot of scattered light. Correcting for that scattered light, we got the first calibration, which was my PhD thesis. We did an upgrade to get rid of these scattered light sources. This upgrade happened after COVID in 2022, and the results ended up in another PhD thesis. We had a lot of small things. If you're interested in systematics, you can find on the way. Here are our publications, a bit to read. Okay, let's look into Scala in detail. We start down here with our light source. What is that light source? We start with a double monochrome from our experience. We originally had just one. We have scattered light, so we don't get monochromatic light, but also a floor of scattered light below. That doesn't really help us. Second, we would like to do the calibration while day, because then we have the whole night for the stars. So what we added was a chopper. We can measure signal and background roughly every 2 seconds. And we have built our own picoampermeters to do so. And we decided to read them very quickly. And that's nice because these cosmics, which hit our photodiode, you can then see and you can correct your data for it. Now we have our light. We need to get that into the telescope. So we have these projector modules. We have 6 of them. Each one is producing 3 beams. Each projector module looks like this. You have an integrating sphere, a baffle, a collimator, and then a photodiode per beam. The baffle you need because each mirror should just see one hole of the integrating sphere. And then you want to measure how much flux we are emitting. And that's the major part here. So how do these photodiodes look like? That's a prototype. You have a 10 by 10 millimeter photodiode, and you have baffles around, which are very important because otherwise you have scattered light. So we need to calibrate those ones. So what we started to do is we bought some NIST photodiodes. We built our own comparator facility. We get the light into a fiber. We send it into a dark box where we have a gantry robot, which can then point the light to the NIST photodiode to the photodiode to calibrate. You fill that up with 12 diodes. You close the box. You come back 2 months later, and you go on. We found a few issues with this system, like thermoreflectance. So we made a new version. That's this one with the light inside. If you have questions, I can show you later a bit more details. The other thing is this baffle. Now it's a 6 aperture knife edge baffle. Before, it was just a plate. And that was a bad idea because you had all this scattered light here, which was seen by the photodiode, but not by the telescope. Now you see just the very thin edges of the knife edges. Okay, last piece. Why do we have this plate on the telescope? Because we want to ensure that we only use the path for the stars, which we also have calibrated. Now, how to do that? You put plates with the right holes for our pattern onto the telescope. And down here you have Simona Lombardo in 2014, when we did that the first time. Okay, a telescope and we put an aperture in front that will result in diffraction. And we can measure that. That's lucky imaging with SNFs. And you see this complicated hexagonal structure because we have 6 modules. Why do we care about it? In the red, we make our telescope diffraction limited. We have a small field of view, so that will carry power out of the field of view. And we need to know how much that is, such that we can properly extract the flux. Now, what are the results? Okay, we have the measurement from the photodiode, so we know how much flux we have sent. We have the measurement from the telescope, calibrated with Carlsberg. So we have another flux, so we can take the ratio. If the ratio is flat, Carlsberg and the SI system agree in color. So let's look for that. The measurement is flat over here. After correcting for all the systematics, we have large uncertainties. In the blue, we were not that successful because of the out-of-band light, because it's very difficult to model and then to correct. But at the end, it was flat to something like 4 millimach over 1,000 angstrom. Okay, now we did the upgrade. We suppressed the scattered light. What do we get? We get this black curve. Again, in the red, it's nicely flat. We have some small scale structure here. So this is the A and B band. There we have second order light from SNFs because of gratings. We have some features here, which you might recognize, that's ozone. And here we have the crossover to the blue channel. For the red, it's flat, which sounds good. For the blue, we have this trend. What is it? It was found by David when he recalibrated the standard stars. There's a temperature coefficient. This here is a band of 5 measurements. If I show you the 5 measurements by day, you see the instrument evolves. It evolves with temperature, and that's because the floor chillers on Hawaii were broken, so the temperature wasn't stable. If we now take this differential coefficient David has found, the measurements line up. Where is this temperature coefficient coming from? We looked into the design of SNFs, we did some metrics, optics, we found it's the refractive index of UV-fused silica being temperature dependent. And that then immediately introduces a wavelength calibration. It's making a defocus in the instrument. The focus curve is not linear, it's parabolic. So to which temperature should we correct? And that's something we're working on. But I can show you that's scaling to the mean temperature. Let's go 2 degrees lower. It's turning flat. And you see that we have to work on that a lot more to understand to which temperature to correct to. All this data is from 2022. What did we do in the meantime? We had 40 observing nights scheduled, and we got 10 on Mauna Kea. High wind, high humidity, okay. Broken floor chiller also, but you can also be unlucky. Mauna Loa erupting. You can have an earthquake on Friday when no one is at the mountain. It cuts your power, everything gets warm, and a week later you can start observing again. And then the last thing, you have a hurricane passing by. It presses the water into the dome, into the telescope, and into our instruments. So SNFs is working again. It's dry and it's doing what it should do. So what do we have? We have corrected the systematics we have found. We have much smaller uncertainties now. It's flat, which is nice for Roman and James Webb because the color agrees. We have some small-scale structure in the pipeline, which we have identified, and we're working on suppressing them. So the next step is then, of course, this temperature coefficient. We have to understand, we have to model, we have to account for this in the pipeline. While the pipeline was developed, we had floor chillers, so they didn't have the problem. Now, one thing we are waiting for more than 10 years for is a recode of the primary mirror. We finally have it, and they are also working on the floor chillers. And I'm concluding with a picture of Benjamin Bastian Querner and me sitting in the UH telescope. Thank you.
We have time for questions, George.
So since Ralph is here, maybe we can make this definitive. I think when you say CalSpec calibration, it's anchored by the Messier point, but I think we ought to confirm that to make sure that we're all talking about exactly the same thing.
I'm not doing an absolute calibration, just a relative. So the color is what I'm looking at.
So it's only the color you're testing here.
The color, not the absolute
The
scale.
absolute you're not testing. Gotcha.
Absolute scale is a lot of work.
Okay.
And it would be great if we had Landolt, because then we truly have a source up in the sky which looks like a star.
Well, let's still put Ralph under the bright lights and verify that it is all anchored by the Messier point from 1995.
Except for a 0.5% correction from the MSX, that's true. So in other words, the Messier is 3.46 and the 0.5% makes it 3.47 at 5556 air wavelength and a 25 angstrom band.
But just to be clear, that completely cancels out.
Yes.
I understand. Okay.
Question online?
Yeah, please.
Yeah, Gary Burstein, since Scala only illuminates a small fraction of the input pupil, how is the calibration transferred from the projector's photodiodes to the full pupil response of the telescope to stars? Is there an error budgeted for this?
So you have this pupil mask here, and we are only using the areas we're also calibrating. All the rest is blocked when we look at stars. So our pupil is shrinking to just a 1 meter telescope.
Yeah, we have that mask on when we look at stars.
And doing the calibration with Scala. It's always on for that purpose, so we are sure it's the same systematic.
So Daniel, I was wondering for Scala, do you have to thermally control your light sources? I mean, do you have the same, or are they fairly robust to the environment?
It's just a xenon high pressure lamp, which works on Hawaii since 10 years. And we had no problems. With a laser driven light source, we would have had problems in the lab. They are dying every 2 years. So, yeah. And we are measuring the flux coming out of the system while exposing SNFs.
Right, so you always have
always
relative calibration.
know how much light we are emitting in the moment we are also illuminating our telescope. And the shutter which is controlling everything is the one on our side and not on SNFs. We open them early and we close them late so that we always have all the light we recorded also on the detectors.
Okay, fantastic. Anyone else? Sorry, I gotta get out of the, not used to the projector working. Yeah, okay. Shot at the ceiling, please.
Yeah, great talk. Before you got to the time-dependent fused silica refractive index mention, you mentioned something about the blue and how the error rose, and you said something about passband issue.
So in the green curve, you mean?
What's that? The green curve,
In
yeah.
the green curve. The issue was we had only one monochromator. So we have scattered light in the monochromator, and what we get out is a line plus a floor of scattered light. And now you go to the blue, you go into the UV, the lamp spectrum is decaying, but you still have the floor from the red. And all that is seen by your photodiode, but you don't see that with the spectrograph because, of course, you just look at the line. And this faint light is dispersed, so you don't find that. So that's the problem if you have out-of-band light. So that's why we have the double monochromator. The first one selects the wavelength, and the second one suppresses the scattered light. And if you want to test that in your lab at home, best thing is you take a color glass filter. They usually have optical densities 5 or higher in the rejection region. You tune your wavelength there, and you take a measurement with a photodiode. If you don't measure that, you have out-of-band light. If you get that low, then your system is working well.
Let's thank Daniel again. Okay, so next up, Joe Rice is going to tell us about what does SI traceability mean for stellar spectral flux calibration. I'll give you like a 5-minute.
Okay, thank you. Can people hear me okay? Okay, so what is this traceability? So I have a few things to talk about here on this definition. So this is a typical definition, a property of the result of a measurement or the value of a standard whereby it can be related to standard references, usually national, international standards, not necessarily, okay, through an unbroken chain of comparisons, all having stated uncertainties. So one thing you notice here is the word units is not in this definition. Now, my talk is about SI traceability, and of course, SI is all about units. In fact, I don't have a slide on the new SI compared to the OSI, but there's a beautiful Wikipedia page that already explains all that. So just go to that if you want a refresher on this new SI that we came up with in about 2018, 2019. But the point of my stressing this, not units, is that traceability is for relative calibration also, okay? It's not just about this talk. Hopefully you don't walk out saying, I'm just going to attach some units at the end. I care about relative, which most people care about relative. The other point I'm going to say is everything's relative. Remember Einstein? In units world, it's the same way. In traceability world, it's the same way, okay? Not units world, but traceability world. Every measurement is relative to some other standard. That is what traceability is. And it's about an unbroken chain. So does something break when I put it on a satellite and vibrate the heck out of it and flash, shoot it to space? Usually. But you have to check that, okay? Astronomy's given up on that notion. Basically, you have the stars, okay? But still, how do we get an unbroken chain? Does the atmosphere break things? Perhaps. Alon's going to talk about some very interesting ways to not have it broken that we're going to capitalize upon in on this STARS project. And the main thing I'm going to talk about, though, is these references that we are comparing to. And what are the national standards references? This is, in a way, this is my outline or my introduction, okay? And I'm going to talk about those references and what are their uncertainties, which happens any kind of traceability, okay? Okay, so what are the fundamental radiometric reference standards? So I give a workshop every so often at a CalCon conference, and it's an all-morning workshop, so I'm not going to spend all that time. But if you go into a room and your job is to come up with a light meter or a light source, and you can't use just buy a laser meter. No, you have to come up with that. What are the physical principles you could use? And by my count, there's 6, although one of them's debatable, okay? So the obvious one everybody likes to use, especially in the infrared, and they're very good in the infrared, is black bodies, the most popular thing. What could be more complicated? You put a black can and put a thermometer on it. Voila, you've got your light source. Put the Planck equation in there. Done. Okay, that's great. It turns out, especially in the optical near infrared, they're not the highest accuracy. I'm going to teach you about this. This is my sort of forte. Electrical substitution radiometers. We'll talk about what those are next. I'll talk about these other things kind of fast. Trap detectors are the debatable things, okay? If you had a detector that was perfectly 100% quantum efficient, or you knew its quantum efficiency through electrical substitution, you could say, hey, I got every photon going in gives me electron going out, I'm done. And you could, if you only want 5% uncertainty, build a trap detector, and between 500 nanometer and 800, pretty much be within 5% uncertainty just by building it with the right kind of photodiodes, okay? Okay, so real quick on the other ones, just to edify you. The synchrotron, we have one of these, and this is actually electron storage ring. You can use the Schwinger equation in a very analogous way to the Planck equation. If you've got a circulating beam of electrons, they emit a cone of light. And we use this actually at NIST for calibration of NASA EUV satellites all the time. You have to know the magnetic field, current, and energy. You put it in the Schwinger, and voila. Very analogous to blackbody. You can count photons, right? Photomultiplier tubes. There's all kind of fancy newer ways to do it. They have Lynch photodiodes. You can correlate them, and you can actually, it's a wonderful method. The limitation is you get a huge background, and you're just time correlating your photons that happen to come out. What happens is a UV light goes in one part of a non-optical, non-linear crystal, and you get 2 photons out because of energy conservation and momentum conservation. You know the direction and energy of every photon that you correlate by measuring one, and you know when there's going to be another one that you know something about. That's a big area in the quantum world right now, but very low flux. You might say, great, but very high background with it, okay? There may be some potential in future for using this in astronomy, but I haven't heard of it yet. Okay, and the last one, radiation pressure, high power. If you got a laser, you can actually weigh the momentum transfer of the photons to essentially a scale. Okay, so those are things people are working on. But back to the more popular, and practically for the minute, the more popular gold point blackbody. Of course, back in the 70s, people used copper point blackbody, which isn't too much higher temperature than this. NIST, we have gold point blackbodies. The scales are through ITS-90. The NIST radiance scales are based upon this, not the NIST irradiance scales, okay, which is FLUX for those that haven't got that conversion yet. We call it spectral irradiance at NIST, and Ralph taught me back in the day. That's the same thing astronomers call flux, okay? Okay, but anyway, what happens is you've got a cavity and you surround it with molten gold, and what you're seeing here as you go through a melt, well, you can go through a melt and then back through a freeze. The ITS-90 tells you the temperature here, you're surrounding your cavity, your emissivity is hopefully 1. It should be measured, but you should measure it, by the way, and that's actually, we're going to come to that, a very important point for the spectral relative stuff, okay? Anyway, basically you get at that temperature a Planck blackbody curve, and it's wonderful. You can apply it to things, okay? So what I'm really going to talk about, because for flux, as I mentioned, we actually trace to electrical substitution radiometry. So what is this? It's basically a balance between optical and electrical power, okay? The principle is simply that you basically are turning both methods of power into heat. And the same amount of heat from fundamental physics, it doesn't matter whether it's coming from laser or star or from a heater. I've got a resistive heater. And so the way it works in practice in my lab is we have a laser, we shoot it into a black cavity, and we close the shutter to get the background, we open the shutter, and we look at, we have a thermometer here, we keep the temperature of this cavity fixed, and we look at the heater power required in the servo loop to keep the temperature fixed as we open and close the shutter. It's a very popular method, actually, not the most popular, but solar irradiance, for instance, has been measured like this since the 1970s. Let me get to the next slide. In cryogenic version, where everything gets to be much better uncertainty, you cool down the cavity to about 4 or 5 Kelvin. It's in a vacuum. You have a Brewster angled window with a polarized laser beam going in there that's tunable across the spectral range. And this is how it looks. It's about 20 millimeters in diameter, about this long, with a slanted black surface with a little chip thermistor, a little chip heater on the back. That's going to be your heater power, okay? And your laser's going to go in, and you're trying to get that little chip heater as close as you can to where the laser hits, okay? Because there is one systematic that I'll talk about that's related to that, which also goes down with low temperature. You can use superconducting heater leads, for instance, so that you know you're not dissipating any heat in the superconducting leads. There's no dual heating, in other words. Lots of little effects conspire. We end up getting 0.02%. And that's K equal 1K, by the way, is similar to sigma. You'll see K all through NIST people talks. It's the nomenclature is, if you think about sigma, that's just statistical. But K is the coverage factor that takes into account what if you're estimating your systematics on a sort of a similar thing, which they might not be Gaussian distributions. Anyway, the point is, when you see K equal 1 or K equal 2, think sigma 1 or sigma 2, and it's good enough for now, okay? Anyway, my goal in life is to get the 0.02% on stars as much as we can, okay? So that's the whole New Stars project, because we can measure light at this level with these kind of detectors. There's lots of reasons why we can't get it to stars, but let's try to work on it and let's see where we're at on that, okay? So that's for the rest of the talk. Just so you know, the uncertainty budget is just so you know the types of things that have to be worried. Not a long list, okay? Basically the responsivity that we actually measure when we are calibrating a trapped photodiode detector. So what we really do is calibrate trapped photodiode detectors. They go out. By the way, I'll talk about that, but the photodiodes that folks here are buying are traceable back through power, okay? Did I mention that the OR system is called, oops, look at this. The one we actually use at NIST all the time is primary optical watt radiometer. That's what that acronym means, or power. That's what I've been telling you about. That is, okay, so the uncertainty in this case is, so to calibrate you, 100 ppm would be 0.01%, okay? So we can actually, in certain cases, get way better than this 0.02% that I mentioned, but more often we get about 0.02% across the spectral range. So international standards labs do intercomparisons every so often. They're organized by the BIPM, the Consultative Committee of Photometry and Radiometry operating out of Paris. And they did one of these back in the 90s to show, so the 5 here is 0.05%, and the uncertainties are the quoted uncertainties by the participants. They sent around trap detectors and in a blind study said, what do you get at these wavelengths for your responsivity or your quantum efficiency of this trap? Of course, we all know it's really close to 1 already, okay? So it's a little bit of a cheat, but you can see there can be systematic. This lab found some problems and corrected it, okay? NIST actually back then was over here, okay, which is why they hired me to make Power. This was Power's predecessor, but they got a little worried when they saw that, okay? Okay, so photodiodes, of course, that aren't trapped, or many of you know this, but those that don't, they have some crazy responsivity versus wavelength. To help you understand the importance of this problem, if you're going to buy a silicon photodiode, that's great, but to do Roman, you got to get out here, and even farther, there are photodiodes that exist, I just haven't shown, to go out here, and there's crazy things. You have to do spectral relative with traceability. That is the point of my talk on these kind of things, which you're going to probably use, like Daniel talked about, at your observatory or close to it, okay? That seems to be the direction we're going in dissemination, okay? Okay, so trapped photodiode detectors I already talked about, but just to show you how wonderful, as I said, between about 600 and 900, they're pretty much a known quantum efficiency if you calibrate them. Basically, a trapped photodiode just means that these are photodiodes that have an internal quantum efficiency of near 100% in this spectral range, but the only problem is they reflect 30% of the light, so you just trap it in some of the photocurrents and you're done, okay? Okay, so that's, the photodiodes can be very stable, okay, over a long period of time, and I have there's lots of data well beyond this that I have, but I'm going to speed up a little bit. One of the things that we want to point out too is besides photodiodes, there are lamps. You can buy a lamp from this of type FEL, and it's basically the way, and as I mentioned, the irradiance of this lamp at 50 centimeters, you can get the spectrum from NIST. NIST will sell you the lamp and say, here's the spectrum we measured. It's very simple, very easy. It's not as popular right now for the astronomers, but basically it does get a scale from Power because you make a filter radiometer. This is actually a fairly narrow filter, but this is a log scale. And it's not super narrow, but it's narrower than 100 nanometers typically. And basically you can, one of the points of this is there is a high temperature black body in this scale, but this is 3000 Kelvin. And we put the scale on it through optical methods back to Power through this filter radiometer. That's the point that we transferred to lamps. Okay, so to sum up then, there's an uncertainty budget I'm not going to go through. Don't have a lot of time left, but we can talk about it later. That's for the lamp calibrations, okay? And this is the intercomparison analogous to what I showed you for the cryogenic radiometers. So by the time those people have lamps, these are all national standards labs, send them around, and NIST is actually the best in the world because of the way we're doing it. Other places aren't as good because of the way they're implementing that. But this kind of thing, these lamps have been in here. Okay, so the final thing I want to talk about is a little bit about NIST stars, okay? Our traceability for NIST stars, and that's one reason I talked about the FEL lamps, so you can understand this. So Susanna mentioned NIST stars. We're planning to go to Chile with it. It did some observations at Hopkins on Vega and Sirius. We need a lot more nights, a lot drier place. We're going to Chile, and eventually, so we're going to be looking, we have a telescope, we'll be looking at stars, and how do we trace back? Well, we have a field light source, a transfer spectrograph, and we're basically, all that gets a scale from back at NIST on an FEL lamp. That's why I told you about lamps. And this is the short version of high temperature black body, but don't think that we got this from Planck's equation alone. We know the temperature from power, okay, of that black body, like I just showed you. Okay, we're working on a new method, which is the next slide that I'll quickly get into, but it's a portable detector base. So we know these detectors ship well, probably better than lamps and spectrographs. So why not use detectors, okay? And that's what this is all about. So if we got a detector like that, in fact, a trap detector in silicon, we have in gas for the longer range, we'd put it on a translation stage looking at something that's an artificial star, but a monochromatic one at a time wavelength artificial star. Basically, this is a subset of the data. It's basically a line source that we sweep through. So we know the light coming out of this at a fixed distance. We know the irradiance, in other words, with our trap detector. Then we swap in anything we want. This light could go to a telescope. Well, right now we're depicting it just as calibrating a spectrograph, okay? And this is actually commercial stuff nowadays. A supercontinuum laser feeding a basically monochromator is how it works. And it's very stable. We're going to try to pilot it along with, like I said, with the lamp-based transfer, and to have 2 chains of traceability, which is always better than 1, to try to check ourselves. Okay, so that's next slide. So my summary is that this flux scales are not based on black bodies. They are based on cryogenic ESRs. And we have the scale these days disseminated is through photodiodes and FEL lamps. And the disseminated depends on tons of details. A lot of this stuff is about details. All the relative calibration is about details, but it can be very good if you do a good job. And I have to advertise that if you have any students about to graduate, we have a great postdoc program at NIST, if you want to work with Susanna. So thank you very much.
We have time for a few questions. So is anybody online? No? Joe, how many power devices do you have? Is there like one gold one well,
NIST has several. By the way, I didn't mention it. It's a backup slide, but the NIST Boulder has had one that they decided, let's go with a flat nanotube instead of a cavity, which doesn't give as good of a absorbance, but pretty good. Okay, and they calibrate against us. So power is kind of the main one, but we do have other ones. And any respectable industrialized nation has at least one of these cryogenic radiometers. By the way, we're moving away from the helium, trying to get our cryo cooler because helium is going to get harder to get. I hope I answered your question, but essentially one. But there's nothing really special about power. If it broke, if the cavity busted, we could just make another one. Okay.
You just go through the same process of calibrating it.
Well, it's primary standard. It doesn't need to be calibrated.
That's what I was wondering.
We do things like we measure. I didn't really stress that. We do measure the cavity reflectance, okay? And that's a relative calibration across a spectral range. So really, if you think about for supernova cosmology, what you need is some reference standard of spectral flatness, okay? So, Ralph's tried his best, but there's models in there, as he's pointed out. So this black cavity that we have at power, which could be replicated and is intercompared, is basically the flat reference standard.
Thank you. Anyone else? Okay, then let's thank Joe again, please.
you like to?
Is it now? Now, Suzuki? Is that? Okay, thank you.
Okay, and next up, now Suzuki is going to talk about black body stars for accurate UV vis IR flux calibration. I'll give you like a 5.
Okay. Thank you very much. It's so nice to be here. So I work on the supernova type 1 supernova cosmology, and every time I start talking about calibration, everybody goes to sleep. But I'm so glad everybody's up and excited. So let me move on. So I recently moved to Florida, and I got a direct hurricane hit here. I was living here. This was my first hurricane experience. Okay. So this is the plot I made 10 years ago, 12 years ago. So we got the 500 type 1 supernova, and we made sure lambda CDM is the case, and the Einstein-Dositta case is rejected by 5 sigma. And then for next 20 years, last 20 years, we are happy with the lambda CDM cosmology case. But the things are getting interesting. This is the compilation done by David Rubin, Union 3. So this is the Hubble diagram, but the residual is deviating from the lambda CDM. So let me magnify this. And everybody talked about this. So 3 groups, Pantheon plus, Union 3, dark energy 5. Everybody showing 2 sigma deviation. And then now, with the DAISY BO data, it's a 3 sigma deviation. So in terms of photometry, this is a magnified version of David Rubin's plot. So deviation from the lambda CDM at redshift 1 looks like it's, let's say, 3%. So to claim 5 sigma, we need to divide 3 by 5, which is 0.6%. So we need a 0.6% precision. That's the requirement to claim 5 sigma deviation from the lambda CDM. Okay? So it's not the only type 1 supernova. So I started my career from the Big Bang nucleosynthesis using quasar absorption lines, namely using deuterium abundance. So I worked hard to calibrate the cake high-res, which is high-resolution spectrograph. And I contacted Ralph 20 years ago. I was complaining that the STIS, HSD STIS, is deviating from my FLUX calibrated data, okay? And this one matters because this range, around 6,000, is the place we want to, this is the deuterium abundance region. We wanted to calibrate this region very, very carefully. The reason was Ralph stitched 2 grisms here. That's why you see the deviation. And the Carlos here has already reported in 2009. This is still happening today, by the way. If you take a close look at the G191, you still have a jump here. And this happens to be inside the B band, which is the most important photometric band for type 1 supernova cosmology. So if you magnify, you can see 1.6% deviation here. So this is where Ralph stitched 2 things. By the way, if you have a high resolution, you see the oxygen 6 emission line. This is not noise. These are real emission lines. Okay. So in my PhD thesis, I did my Big Bang nucleosynthesis measurement. And then Ryan Cookie, who is my competitor, contacted me because he faced the same problem and he wanted to fix it. And he revised our measurement 10 times better. And I'm happy to report CMB and the Big Bang nucleosynthesis agrees within 0.5%. So first 3 minutes to the 380,000 years, cosmology is okay. Something weird is happening after that. So that's my interpretation. And I teamed up with Ryan. So once again, I was working on the quasar team, and for the SON Digital Sky Survey 3, I was visually inspecting lots of millions of quasar spectra. And all of a sudden, I happened to encounter this one. So this is the moment of Zen. So this one, quasar team rejected, of course, but it was targeted as a quasar. And I was shocked. What's this? And I was excited. I thought I discovered Hawking radiation. So, but the Gaia destroyed my dream because it's nearby white dwarf. But I checked yesterday, so as of today, this one is still classified as quasar in SDSS database. So I got interested in, and then I got the chance to present this at Princeton. And Scott Tremaine said, "Oh, you found the Dyson sphere in front of Friedman Dyson." And he was smiling like this. And Jim Peebles said he was surprised we don't see any lines. Any astronomer should be shocked because even if you have 1 millimeter of atmosphere, you should see a sharp observation line. And I was shocked. And Jim Gunn said, now this is the only object which is new to him, because the SDSS, one of the disappointments for him, he didn't discover something new. We knew Lyman galaxies, we knew quasars, we knew many strange stars, but for him, this is new, so I pleased him. So I checked all of the spectra, including quasars and stars, and only 17 survived, okay? I checked everything, which if they are consistent with the black bodies. And this is just a pure, plot in log scale in Y. And you recognize something strange, which is they are all parallel. That means they happen to be the same temperature. I didn't require any constraints. I just looked for the featureless black bodies, and they happen to be the same. And the Gaia gives me the distance so that I can get to know the radii. And they are all same size. Strange. Okay, so we published, I teamed up with Masataka Fukita. Those who work on this area, you know him. He's the one who established SDSS filter system and converted from Vega to AB system. He's a little bit, I wouldn't say that, but Ralph and Ralph, I think he's retired, so I can say that. He referred 13 of your papers. So he's the one who is giving her time. So we reported this, and originally I named perfect black body, and Fukita-san said, Mr. Suzuki, in nature, the concept of perfect doesn't exist. But in his article, he quoted perfect black body, so I think I'm winning. Okay, so with the other data, Pan-STARRS, Galaxy, SDSS, and Gaia, they are consistent. And I was a little bit concerned of why Gaia data is off, but if I introduce the correction, I think it's going to be okay. So many people concerned about the infrared excess, so I checked with infrared data, and this is WISE, just for your information. I'm not fitting. I just simply extrapolated, and the WISE data happens to be right there. Okay, so I was pleased. And then many of them, actually 17%, they got the infrared access, so we rejected them. Okay. Then Chris Stubb, I think, introduced this a few years ago at the LSSD meeting. So he didn't like the idea, we don't understand this. And somebody, Aldo Serena, he studied the nature of this black body star. So many complaints I received from white dwarf community. Why this is new? Because it's known as DC stars. But if you plot color diagram, DC stars are everywhere. So these green data points are all DC stars, which is featureless white dwarf. By the way, the definition of DC stars is very weak. But this black body stars is right on this straight line. Okay, so it's not DC white dwarfs. They are special. Okay, so he studied the conditions, and it happens to be one condition. Certain cooled helium star can be very similar to black body star. So actually, our black body star is better than his model in terms of black bodiness, but theory can back this up, so it can exist. Okay, so this is the spectrum. This is the SED of photometry. So Ryan Cookie, who I mentioned, working on the, originally he was my competitor, but now he became a great friend, and he got interested in, and he searched all of the Gaia data, northern hemisphere and southern hemisphere, and using XP spectra and the photometry from the Ys, we excluded the infrared excess, and he got the 441 candidates. Okay? So I myself and Ryan Cookie observed them all. So calibration work is very hard. We don't want to sacrifice a grad student's life or a postdoc's life. So we did it all by ourselves. So I observed like 20 nights a year. So, so these red ones are rejected one, okay? So the good one, we colored green. So only 1 in 20 satisfies this criteria. So one exposure is like 40 minutes. So we spend many, many hours on this. So then we are running ongoing one is the HST program. And if I may, I wish to propose to go on the JWST and let me tell you what we can do. So HST ones, we got the time, and I have been scratching in my head for 3-4 years because the last observation was 2020. We got the glitch, and the 21 was the last. So to my disappointment, the measurement was a little bit off, but based on your talk, so we can fix it. And I checked last night, and it goes to the right direction. So I'm so glad. I should be confident. I could have reported to you earlier. Then this is the constraint. So black body needs only 2 parameters. One is temperature, the other one is amplitude, which turns out to be angular radius, apparent angular radius. So this is the current constraint. So temperature doesn't change much in terms of photometry because it's a radiating tail. It doesn't change much. This is the only change which affects the photometry. So as of today, we have already achieved the 1% level, actually less than 1%. So if HST, I did the simulation before, so we can shrink the contour. With JWC, I can shrink more, okay? So if I do today with the PANSTAS and DS data, I can claim any photometric band, I can predict 0.6% accuracy. Near future with HST, I can do 0.3. UV part is helping. JWST, I think we can do 0.1% for the best black bodies. And Ryan Cookie is one of the developer of PIPIF, which is the reduction pipe case developed by Jason Projector. It's already there in the developer version, so anybody who is going to reduce the spectra can use this black body. So last time, Chris Staff said, I didn't like your black body, but on the 3rd day, he said, this is what I call don't understand trilogy. I don't mind using what I don't understand, which is black body, because we use type 1s supernova, which I don't understand, or dark energy, which I don't understand. So I don't understand trilogy is complete. Okay, so this is my last slide. So proposal to you. Color spec is of course the one, and please consider adding this black body stars. And I have 3 dozen candidates to refine, so I still need 1 more year to complete our observation. But in 1 year, our best, we can send you the best black body candidates. So, and one more thing, I got some high resolution spectra which doesn't match to the DA white dwarf model. So please try to make use of high resolution spectra for your modeling. And let's do the healthy competition so that we can discuss why we disagree and not accusing, pointing the finger who is wrong. So I think I'm curious to know if this is a perfect black body. And I propose, every 4 years is a good cycle because it matches to the PhD student cycle to update the database. So I don't want to hear the updates right before publishing the paper. So it'd be nice. And if you guys remember, this meeting, nobody mentioned, was scheduled 4 years ago, right? 2020. And then we had to postpone, and I wish to see Ralph Bowling Fest in the future.
Okay, questions for now?
Yeah, shout at the ceiling, please.
So how do you determine the uncertainties? So, you could call anything, perfect is, since everything is relative, you could say perfect is relative. If you define it as a perfect black, well, if you define then, why not zero error? So what are your, what are you using to determine the uncertainties?
Yeah, so this is the criteria. So we are shrinking this, and as long as this contour shrinks, I claim it's nearly black body. So black body with certain uncertainty point something %. So in Fukuita-san's paper, he says nearly black body, so perfect black body. But I claim I can, this is very cheap because it's free, it's for everybody, and only 2 parameters can give you sub% precision.
Let's say SDSS and Galax and WISE all were systematically shifted in some way from truth as defined, truth as truly defined in SI, say you could, would this still be an okay way, how do you say, what would happen then?
So I forgot to mention. So I teamed up with the French team. As you know, that unit has to be done by French people, kilometers, kilograms. And as Susanna mentioned, that a standardized team is measuring absolute independently. And these stars are being observed by standardized. So I can get the absolute value as well, totally independent.
Okay. I figured you might have a question.
So I'm curious, though, what's the limit on this? Is it the distance from Gaia? Is it going to be the final limiting on the accuracy possible?
So if Gaia can measure the parallax better, we can shrink this one. And this is almost equivalent of the amplitude of the this one. So the radius and distance is the same thing. So if you JWST can do the parallax measurement as well, we can do much better than Gaia. And we can shrink this contour dramatically.
You don't have any interstellar extension in any of these?
So these guys are very nearby, so I don't expect to see too many extinction. However, there is a degeneracy between extinction and temperature, so it cancels out. It's self-built. So these are the distance guide. So 75 parsec, so 200 parsecs. It's within order of a few hundred parsecs. We on purposely choose nearby ones.
Is it possible that the ones that you have rejected might be affected by extinction?
Might be within 100 parsec scale, but parsec.
Yeah. Let's see who. Sorry.
First.
Who's for? Oh, Kathleen. Yeah.
Okay, yeah, on your future observation, you have it pushed out to about 3.5 microns. Is there any hope for getting further into the infrared for these?
Yes, I did the JWST MIRI calculations. So if you can afford 1 hour, I can get down to % in MIRI, which I don't think nobody can do, I claim.
Okay, yeah.
How many total are there that you have now? And
So-
where are they on the sky? Is that what?
So since we got the Gaia, so it's both northern hemisphere and southern hemisphere. Currently, the best candidates 3 dozen
And are they
everywhere.
So we have them north, south, and
Yeah. So I'm happy to
out of the
give it to
galactic
you.
plane.
Yes, I can tell you how bad or how good your Oxtel telescope is.
Sophia, does anybody online have a? No.
Okay.
Gerard.
If that angular size could be measured, how well would it have to be measured to be meaningful?
This is already meaningful because I impressed myself. Where is that? Oh, sorry. I didn't prepare that I have a table of the radius. So this is only 0.5% in radius. I can get to know the radius in 0.5% as of today. So if you can, do the JWST or HST, we can get to know 0.1% in radius.
Susanna?
I just want a clarifying comment. Stardust doing
He's observing this.
color,
Yes.
okay, not absolute flux. Sure.
Anyone else? Yeah.
So the temperature of all of the ones that you have seem to be identical to which degree, to which extent?
So 160, 652 plus minus 50 Kelvin.
Wow. And can you give us some brief hints on what Aldo Serenelli's model revealed about the nature of the white dwarf? Or white
Tried, so he can reproduce featureless white dwarf. So his theory is a cool heavy white dwarf.
Well, Kevin, well, let's do Kevin. He has an answer. Yeah, please.
So do you have any ultraviolet spectroscopy for any of these? Because if
we are taking spectroscopy. So that's why we are spending lots of nights. So these are all spectral, for instance, these are the extruder cast, and these are all spectrographs. So we are getting the good ones, we are aiming to get the signal to noise ratio 100. We still don't see features.
any ultraviolet?
Ultraviolet, I don't know your definition, but our spectra starts from 3300 angstrom.
If I was going to look for weak lines, I'd look in the ultraviolet.
Yes.
Might get some diagnostics.
Yeah, we need HST.
HST.
Yes,
But that's also where it drops, right?
that's right.
It's gonna be
Yeah,
very.
but I know it's hard, but
Yeah.
be where you look.
But as of today, the blueprint is behaving very well.
Is that a population fit, or do you have an individual radius for each one?
What do you mean, population fit?
Like, is that contour, was that for one of them or for the?
That's one of them.
Okay.
Each individual star has that contour.
Okay, so I think now would be a good time for.
One last question online.
Please, yeah, let's yeah.
So Brett Morris, how bright is the brightest candidate star in the optical?
So 14.5.
Okay, so let's thank now and all the speakers.
Copy and poster.
And come back when?
Half an hour.
In half an hour.
To the agenda. We're on track.
Yeah. 10:50.